How a CPU is manufactured. From sand to pure silicon, every CPU begins its journey from ordinary sand. Sand contains silicon dioxide, SiO2, the primary raw material used to make a semiconductor chips. Through several purification processes, the silicon is separated from oxygen and refined to an extremely high purity of 99.999%. The ultra pure silicon is essential because even microscopic impurities can affect the performance of billion of transistors inside a CPU. Growing a silicon crystal silicon ingot. Here the purified silicon is melted inside a quartz crucible at temperatures above 1400 degrees Celsius. A small seed crystal is slowly dipped into the molten silicon and carefully pulled upward while rotating. Here, this process is known as the Czochralski process. Forms a large, perfectly aligned cylindrical crystal was a silicon ingot. Maintaining a single crystal structure is crucial because it allows electricity to flow uniformly through the processor. Wafer manufacturing. Here the silicon is ingot is sliced into extremely thin circular discs called wafers, each about 0.775 millimeters thick. These wafers are polished until they have a mirror like finish. A perfectly smooth surface is necessary because billions of microscopic transistors will later be built on it. Each wafer can eventually contain hundreds of individual CPU chips. Cleaning the wafer. Here, before fabrication begins, every wafer is thoroughly cleaned using ultra pure water and specialized chemicals. Since modern transistor sizes are measured in nanometers, even a tiny dust particle can ruin an entire chip. This is why CPU manufacturing takes place in highly controlled clean rooms where the air is thousands of times cleaner than a normal room. Engineers wear full body protective suits to prevent contamination. Photolithography, printing the CPU design. Here, this design is the heart of CPU manufacturing. First, a light sensitive material called photoresist is coated onto the wafer. Then, a photo mask containing the circuit design is placed above it. Powerful deep ultraviolet or extreme ultraviolet light is shine through the mask, transferring the incredible tiny transistors pattern onto the wafer. These patterns are so small that thousands cloud fit across the width of a human hair. Etching and doping. After the circuit pattern is created, unwanted materials is removed using plasma etching, leaving only the required structure. Next comes ion implantation, where atoms such as boron or phosphorus are accelerated into the silicon. These processes changes the electrical properties of selected areas, creating the p-type and n-type regions that form the transistors. These tiny transistors act as electronic switches, turning electrical signals on and off billions of times every second. Building billions of transistors, the lithography, etching, and dropping and doping processes are repeated dozens of times to build layer upon layer of microscopic structures. Modern CPU contains tens of billion transistors, each only a few nanometers in size. These transistors work together to perform arithmetic operation, execute transaction and processes data at incredibly high speeds. Metal interconnection. Once all the transistors are built, they must be connected together. Multiple layers of microscopic copper metal wires are deposited on the wafer to form an intricate network of electrical pathways. These interconnections allows billions of transistors to compute, enabling the CPU to process complex calculation in fractions of a second. Testing and wafer dicing. Here, before the wafer is cut, the automated probe station tests every individual chip to ensure it functions correctly. Defective chips are identified and marked a precision diamond and saw or laser then cuts the wafer into hundreds of separate CPU dies, each containing a complete processor core ready for packaging. CPU packaging and final testing. Here, each CPU die is mounted on a substrate connected using microscopic solder pumps and converted with a metal heat spreader to improve cooling. Here, the finished processor undergoes rigorous electrical and thermal testing to verify its performance, power consumption, and stability. Based on these results, manufacturers classifies the chips into different performance categories before packaging and